Okay, let's dive in then.
Right.
Today we're tackling speed, distance, and time. Really fundamental concepts.
Absolutely. They're everywhere, really, how things move.
Yeah, and we've got some source material here. It's almost like a reference guide, laying out the core ideas.
Mm,
So our goal is to, unpack that, not just define terms, but see how they actually work in practice.
exactly. Make it real. So speed itself, at its most basic, it's just the rate you cover distance, how much ground and how much time.
And the formula everyone sort of knows is speed equals distance divided by time.
That's the one. And the beauty is, like the sources point out, if you know that, you can figure out the others.
Right, just rearrange it. So distance is speed times time.
Yep,
And time. That's distance divided by speed. Those three are our toolkit, basically.
precisely. But a key thing the material stresses units. You got to be careful there.
Oh, yeah. Meters per second or kilometers per hour. Those are the common ones.
And you can't mix and match carelessly, right? The formulas only work if your units line up. Kilometers need hours. Meters usually go with seconds. Consistency.
Got it. That makes sense. But, things rarely move at one perfectly steady speed, do they?
Not usually, no. That's where the idea of uniform speed comes in, covering the exact same distance in each equal time chunk. Think cruise control on a totally empty road? Maybe.
Maybe. More often it's
Yeah.
variable speed, right? Speeding up, slowing down.
Definitely. That's most real-world movement. City driving is a perfect example, or even just walking. You slow down, speed up.
So if the speed's bouncing around, how do we talk about the speed for a whole trip?
Well, that's average speed. The
Yeah.
sources define it clearly. It's the total distance you covered divided by the total time it took.
Okay, so it smooths out all the stop, start, fast, slow bits.
Exactly. It gives you one single speed figure for the entire journey, often much more useful.
Right. And sometimes we need to swap between those units, kilometers and ems. The sources mention a shortcut.
Yeah, a very handy one. To go from kilometers per hour to meters per second, you multiply by 518.
5 over 18. Okay.
And the other way, meters per second to kilometers per hour, you multiply by 185 out.
Why that specific fraction, 518?
Well, it comes from the base units. 1 kilometer is 1,000 meters, right?
Right.
And 1 hour is 3,600 seconds. So 1 kilometer is really 1,000 meters per 3,600 seconds.
I see. 1,000 over 3,600.
Yeah. Simplify that fraction. Divide both by 200, you get 5 over 18. It's just the conversion ratio.
Clever. Okay, that makes it much clearer. Now, the material had some interesting examples, like trains passing things. It matters what it's passing.
It does, yeah. Passing a single point, like say a signal post, is different from passing a long platform.
How so?
Well, think about it. To pass a tiny post, the train basically needs to travel its own length, right? From the moment the front reaches the post until the back leaves it.
Okay, the distance is just the train's length.
Exactly. So that example, a 160-meter train at 72 kilometer hour. First step,
Units, convert the speed. 72 kilometers times 518.
which gives us 72 divided by 18 is 4. 4 times 5 is 20. So 20 meters per second.
Right, 20 meters. And the distance is the train length, 160 meters.
So time, distance, speed. 160 meters divided by 20 meters.
That's 8 seconds, okay.
But now what if it's passing, say, a 200-meter long platform?
The train has to cover more ground relative to the platform.
Precisely. The front of the train reaches the start of the platform, but it's not fully passed until the back of the train clears the end of the platform.
So the front has to travel the platform's length plus the train's own length.
You got it. The total distance for the calculation becomes length of train plus length of platform.
So for our 160-meter train and 200-meter platform.
The distance is 160 plus 200, which is 360 meters.
Okay. And the speed is still 20 meters. So time is 360 divided by 20.
18 seconds. See how changing the object being passed changes the distance in our calculation?
Yeah, that's a neat distinction. It's about clearing the entire object. And finally, the sources briefly mentioned objects moving relative to each other.
Right. If two things are moving, the distance between them changes based on their speeds and directions.
Makes sense.
If they're going the same way, the gap between them grows based on the difference in their speeds over time.
Okay. Faster one pulls away.
Yep. But if they're heading in opposite directions, the distance between them increases based on the sum of their speeds times time. They're moving apart faster together.
So it all comes back to those basic speed, distance, time formulas, just applied carefully to each object or situation.
It does. It shows how powerful these simple relationships are. You can break down surprisingly complex motion if you define your distances and keep your units straight.
Yeah, it's pretty elegant, actually. So just thinking about this uniform versus variable speed, maybe something for you listening to consider. Think about your journey today, your commute, or even just walking around.
Hmm.
Was your speed constant, perfectly uniform? Probably not. What things made it change? Stop signs, hills, other people? Just something to notice next time you're moving?